All right, let's get right into it with one of the most mind-bending questions in all of physics. Sounds a bit like science fiction, right? But what if the answer is yes? In this explainer, we're going to unpack a pretty wild theory that suggests just that. A model for how you can get, well, everything. All the stars, the planets, you and me, from literally nothing. So, how is that even possible? Well, to get our heads around it, we can't start with stuff like matter or energy. No, we have to start with the stage itself, with space-time. We got to look at the hidden rules, the deep-down physics that govern the very fabric of reality. Okay, so to see how this all builds up, we have to start with the fundamental rules, what physicists call symmetries of something called Minkowski spacetime. Just think of it as the default setting for the universe, a perfectly flat, empty stage. It's the backdrop for Einstein's special relativity. You can think of these symmetries as the unbreakable laws of a cosmic game board. I mean, no matter how you move or where you look from, some rules just don't change. And the most famous one of all, the speed of light is always the same for everyone. So these rules of the game come in a few different flavors. You've got moving from one place to another, physicists call that translation. You've got changing your orientation, that's rotation. And then there's changing your velocity, which they call boosts. But here's where it gets really amazing. These aren't just some abstract mathematical rules. Nope. In the quantum world, they literally give birth to the physical properties of everything around us. And right here, you can see that connection, plain as day, that symmetry of translation. The simple rule that the laws of physics are the same here as they are over there. That gives rise to what we actually experience as mass. And the other one's rotation and those boosts, they're responsible for a particle's spin. I mean, think about that for a second. This is a huge idea. Mass and spin aren't just properties that particles have, they're direct consequences of the shape, the very geometry of space-time itself. Okay, so up to this point, all these rules we've talked about, they apply everywhere, all at once. They're what we call global. But then along comes Albert Einstein, and he completely changes the game by asking a deceptively simple question. What if a rule only has to apply locally, just point by point? And that shift in thinking, that is the absolute key. See, a global symmetry is super rigid. It's like picking up the whole chessboard and rotating it. Everything moves together. But a local symmetry, that's way more flexible. It's like moving just one single chess piece. You can have different changes happening at different points. And this is what allows the stage, space-time itself, to stop being a boring backdrop and become an active player in the game. And guess what? That's exactly what Einstein did. He took that symmetry of translation and demanded that it hold true locally at every single individual point in space-time. But to make the math work, he was forced to introduce a new field to kind of smooth things out. And that field? That's what we call gravity. Boom. Just like that, space-time goes from being a passive, flat background to an active, dynamic thing that can curve and bend. So this leads to a really powerful question, right? It's the question at the very heart of this new theory. If making just one of these symmetries local gave us our entire theory of gravity, what happens if we do it to all of them? You see, to even try and answer that, we have to go beyond general relativity. To make those rotation and boost symmetries local, you need a new piece of the puzzle. You need a more complete theory of gravity. And that logical chain of thought, it leads us straight from Einstein's original work to a bigger, more comprehensive framework called Einstein-Cartan theory. It really is the next natural step. It takes not just translation, but also rotation and boosts. And to make it all work, it has to introduce a new geometric property, a property called torsion. Okay, so if you think of gravity as space-time curving, then you can think of torsion as space-time twisting. It's a perfect analogy. Just like mass and energy tell space-time how to curve, the spin of a particle tells space-time how to twist. And adding this idea of torsion is the final piece we need to make all 10 of those space-time symmetries local. And this is where the theory takes a really dramatic, unexpected turn. Because it doesn't just add new fields or forces to the mix. Oh no, it completely rethinks something we thought we basically understood, the black hole. The argument here is that conventional theories kind of have it all backwards. See, in standard general relativity, the math allows for a black hole to exist in a totally empty vacuum. No matter, no energy, nothing. But this theory says, hang on, that's a bug, not a feature. A solution without a source? That just shouldn't be possible. So the proposed fix is, well,
It's incredibly elegant. It says, black holes don't just pop into existence from nothing, they only show up where there are particles. In fact, it flips the whole script. An electron isn't some little ball that has mass and spin. No, in this view, an electron is the space-time geometry of a tiny rotating black hole that just happens to have the exact mass and spin of an electron.
So, the big question. How does all of this come together to build an entire universe from an empty vacuum? The answer, it turns out, lies in a sort of mathematical cheat code that manages to simplify the unbelievably complex physics.
This framework is called the Kerr-Schild geometry, and what it does is give us a very special way of describing the spacetime around a rotating black hole, which, remember, in this theory is a particle. And, as luck would have it, this particular piece of math has some incredibly convenient properties that make this whole thing work.
And the absolute number one key property is that it makes the equations of general relativity linear. Now, that might not sound like much, but trust me, it's a huge deal. Normally, the equations for gravity are a total nightmare. So complex, you can't just add two solutions together and get a third one. But with this Kerr-Schild trick, you can. You can literally take the space-time geometry for one particle, add it to another one, and just keep going, building up the entire geometry of the universe, piece by piece.
And what this creates is this beautiful, self-sustaining loop. It goes like this. First, an observer, or an observation, causes a field to collapse into distinct particles. Step 2, the Kerr-Schild geometry is calculated for every single one of those particles. Step 3, all those little geometries get added together to create the total curved spacetime of the universe. Then, the fields propagate through that new spacetime, which then tells them how to behave and collapse the next time around. It's this constant feedback loop. The actors build the stage, and then the stage tells the actors where to go.
So, what does this all mean? Ultimately, it means the universe is basically simulating itself into existence. We saw how the basic rules of empty space give birth to mass and spin. We saw how making those rules local creates gravity. And now we see how treating particles as tiny black holes allows all of reality to emerge from a computational loop running on nothing but the vacuum. All the everything we see around us, it's just the result of this process, pulling itself up by its own bootstraps. And that really is the mind-bending thought this theory leaves us with. It suggests that reality isn't some static thing out there for us to discover. It's an active process, something that's constantly unfolding. And, if it's a computation, it doesn't need some giant external computer to run on. The universe is the computer. Its own evolution is the program it's running. A totally complete, self-contained system that builds everything from nothing.